We're going to take a look at some more tests for convergence. We're going to look at what we call the integral test and the p-series test. All right, so just to recap what we've seen so far, we have the nth term test for divergence. So when we first look at a series and we're trying to determine if it converges or diverges, we can take the limit as n goes to infinity of a sub n, and if that limit does not exist, or if that limit is something other than 0, right there we can say that the series diverges. If that limit approaches 0, the series might diverge, it might converge. We have to look at some different tests to make that determination. So that's where the geometric series test comes in. If our series happens to be of this form, where we're multiplying each term by some common ratio r, the series converges if r is less than 1, and it converges to a over 1 minus r. We have a telescoping series. That's a special type of series where all of the terms in the middle cancel out, and that converges to the first term, b sub 1, minus the limit of b sub n plus 1. Okay, so now we're going to take a look at what we call the integral test. And recall that when we first studied integrals, we looked at them as a sum of rectangles as an approximation. So if we take a look at this curve here and we put these rectangles touching on the left-hand corner underneath, we use those rectangles to approximate the area. And it turns out that if the area under a curve is finite, then the corresponding series is finite. Now, in order to apply the integral test, we have to check a couple of conditions. Let a sub n equal f of n. So our terms of the series are given by some function of n. And if we used x instead of n, we would have a continuous function. That function would be positive, and that function is decreasing for all values of x greater than some value of n. So eventually, the function needs to be continuous, positive, and decreasing. If we have those conditions met, then the series of a sub n and the integral from n to infinity of f of x have the same behavior. They both converge or they both diverge. All right, so we want to know if this series converges or diverges. Well, first let's check the conditions for the integral test. We turn this into a function f of x, and we can rewrite that function using a little bit of algebra here as 1 over x to the 3 halves. This function is positive for all values of x greater than 1. It's continuous for all values of x greater than 1. We also need to verify that it's decreasing, and we can do that by taking the derivative and realizing that for all values of x greater than 1, this will be negative, meaning f of x is decreasing. So we have all of the conditions necessary in order to use the integral test. So now that we've verified that f of x is positive, continuous, and decreasing, we can go ahead and apply the test. We can take the integral from 1 to infinity of 1 over x root x, take the limit as b goes to infinity of the integral from 1 to b, change that to x to the negative 3 halves, take the antiderivative and evaluate from 1 to b, and that ends up giving us 2. Since the integral converges, the series must also converge. The integral we know converges to 2. The series doesn't necessarily converge to 2. It converges to something else, but we do know that it converges. So we can state that our series, sum from n equals 1 to infinity of 1 over n root n, converges by the integral test. Okay, now this will lead us into what we call the p-series test. And you've actually already seen this when we looked at improper integrals. We're making the connection now, since when an integral converges, the corresponding series converges. We can use that same test to determine convergence of series. So if we have a series of the form 1 over n to the power of p, that converges if the corresponding integral converges. And we can go through and verify for which values of p this will converge by taking the antiderivative and evaluating. And now we have to consider what conditions are going to be necessary for that part right there, b to the power of negative p plus 1, to converge. Well, it's going to converge if that exponent is less than 0, which means p is greater than 1. It's going to diverge if negative p plus 1 is greater than or equal to 0, and that means p is less than or equal to 1. So here's our p-series test. Like I said, same conditions you saw with improper integrals. So the p-series test is really just an application of the integral test, but it allows us to avoid having to go through all of the work of actually evaluating the integrals. Okay, so we have the harmonic series here. This is a special series, 1 over 1 plus 1 over 2 plus 1 over 3, and so on. Well, now we know that that diverges because that's a p-series when p equals 1. It's going to take a long time for the sum to get very big, but it will just continuously go up and up and up as n gets larger and larger.